Good morning, everybody. So I thought I'd talk this morning all about evidence for my quantum gravity hypothesis. And for those of you who don't know, my quantum gravity hypothesis basically states that for all massive macroscopic objects, there's this huge cloud of tunneling electrons surrounding them, which is the gravitational field of those objects. So for instance, surrounding the sun, we find a huge amount of electrons there tunneling, and we find also a huge amount of trapped radiation around the sun in its corona. And this is caused by light bouncing between the electrons in the sun's gravitational field and bouncing back towards the sun, and hence it traps this huge amount of radiation there, causing the corona of the sun to be up to 1.5 million degrees Kelvin or so, or even hotter than that in some cases, up to 3 million degrees Kelvin, I should say. And this causes the corona of the sun to be so much hotter than the photosphere of the sun, which is only about 5,700 degrees Kelvin. And when objects approaching fall into the gravitational field of the sun, the electrons in the sun's gravitational field, those tunnel to within the electroweak range of the protons in the sun's gravitational field and exert a force of attraction over those protons. So this causes the force of gravity to manifest over a distance. It's caused by tunneling electrons, basically. And the evidence that I wanted to talk about today for this hypothesis comes from neutrinos and neutrino observations. So the neutrino observations that we've made of supernovae started in 1987 when we detected bursts of neutrinos coming off stars that are going to supernova, arriving earlier on Earth than the light coming from the supernova. So this is really what we shouldn't be expecting, because neutrinos have mass. They have photons arguably have mass as well, but neutrinos have a lot of mass compared to what the mass of the photon would be. So if anything, we should be expecting neutrinos to be arriving later than the light coming from the supernova via general relativity, if gravity just comes down to different masses attracting one another. And if it's all dependent on mass, then we should be expecting the neutrinos to arrive later than the light coming from the supernova, but that's not what we observe. We observe the neutrinos arriving before the light coming from the supernova. So what's happening here is that the electron density surrounding a star as it goes into supernova is also collapsing along with the supernova, the star going into supernova. So the light that's trying to escape from the supernova is being constrained by this electron density that's collapsing. And the electron density is basically falling back in on the star, and the light can't escape because it's bouncing into electrons in the background from the star's gravitational field, whereas neutrinos aren't affected by a background of electrons at all, and those just pass straight through. So this is how we go about testing for my model of quantum gravity, and it's a lot easier to test for than string theory. What we'd have to do is to put neutrino detectors around the solar system, and try and detect a neutrino wind coming off the sun. Since if general relativity is correct, if it's just to do with the curvature of space-time and masses attracting one another, and it's nothing to do with clouds of charged particles and so on, which is what I would predict, then it would be possible to detect neutrinos being deflected by the sun into other parts of the solar system, and we'd be able to detect that with neutrino detectors. So this is how we'd go about testing for my quantum gravity hypothesis. It provides a lot more testable predictions than string theory does. And yeah, another way we could go about doing it is just to see if a neutrino beam is affected at all by a gravitational field, which is an experiment we could do on Earth, actually. We could do that in our laboratories at the moment, I'm pretty certain, or it shouldn't be too much of a problem to do that sort of experiment, I don't think. Since we have like the Gran Sasso Observatory in Italy, and I think with the Gran Sasso Observatory in Italy, they fired neutrino beams through this many miles of tunnel through a mountain, and it wasn't augmented by the gravitational field whatsoever, which is a little bit strange considering that neutrinos have mass and that masses attract one another right in this model of gravity that we have at the moment, general relativity, but on the quantum scale that seems to not be the case. Quantum objects such as neutrinos seem to obey different rules to the ones put forward or the ones exposed by experiments in physics. So yeah, this is how we go about testing it. And this is, yeah, my prediction. My prediction is that gravitational fields wouldn't affect the trajectory of neutrinos through space whatsoever. There is one way, however, in which these clouds of tunneling electrons would be affecting the behavior of neutrinos, if you like. They'd be causing neutrino flavor oscillations, which is this effect whereby neutrinos travel through space and they oscillate between different flavors, between different types of neutrino. So you get a tau neutrino, muon neutrino, and an electron neutrino. Those change between one another seemingly spontaneously. But what I think that's caused by is caused by the exchange of neutral currents between neutrinos in the background. This background tunneling electrons that I describe causes neutrino flavor oscillations by exchanging Z particles with the neutrinos that are traveling through space. So the Z particles impart some more mass to the neutrino as it passes through space, or changes its behavior somewhat, or augments its behavior, causing it to jump between different flavors or type of neutrino. So that's what I wanted to talk to you all about today, the ways in which neutrinos are not affected by gravity or are affected by gravity. Via general relativity, just to recap, the neutrinos from supernova should be escaping after the light has escaped the supernova, because neutrinos have mass, of course, so their progress through space should be slowed down and impeded by gravity, by the curvature of space-time, which is what I think isn't happening, and it's clearly not what we observe. We observe neutrinos arriving before the light comes from a supernova, so that's already very suspicious. That already exposes something of a hole in general relativity, I think. And yeah, we should be expecting to see the neutrinos arrive later than the light, but that's not what we observe. And yeah, the methods of testing neutrinos that we have at the moment, testing for this gravity hypothesis, we could put neutrino detectors around the solar system to try and detect neutrino winds being deflected by the sun, trying to detect the curvature of space-time, channeling neutrinos around the sun and into different parts of the solar system, and try and detect, how neutrinos behave in space that way according to general relativity. But yeah, as I said, that's not what I think is going on. I think that gravitational fields are an electron density, so that a cloud of electrons, i.e., so that when neutrinos pass through them, they just pass straight through, but they may have a flavor oscillation. They may change between different types of neutrino going through a gravitational field. So that's roughly what I wanted to say about neutrinos and gravitational fields. I hope you enjoyed this video. I hope you give it a like, share, and subscribe if you really enjoyed it. And yeah, I hope to see you all soon. Thank you very much. Bye.